Now I'm going to demonstrate how to do a simple Hardy-Weinberg problem. So our original question is, in a small population, in a small village, 15% of the population is born with sickle cell disease, which is a homozygous recessive disease. Our first question asks, what is the frequency of the A allele, A being the dominant trait? Now to find this, we have to find P. So we can use our equation Q, or P plus Q equals 1. But what we are given out of our original information is actually Q squared, which is 0.15. Now to find Q, we simply take the square root of 0.15, which equals 0.387, which, like I said, is our Q. So we can take that value and plug it into our equation. So now we have P plus 0.387 equals 1. Then we simply subtract 3.87 from both sides, and we are left with P equaling 0.613. So now we have, out of this equation, we found the frequency of the dominant allele, which is P. Going down, number 2, what is the frequency for the lowercase p allele, which is the recessive allele? Now, we automatically found that in our first equation by finding Q. P is recessive and also is Q. So, Q is equal to 0.387, which is our recessive allele. What are the genotypes? What are all three genotype frequencies? Now, the three genotype frequencies are homozygous dominant, heterozygous, and homozygous recessive. For each of these, P squared is homozygous dominant, 2PQ is heterozygous, and Q squared is homozygous recessive. P squared we find by simply taking our first value from the first equation, which was 0.613, and squaring it, which gives us 0.376. And that would be the value, that would be the frequency of having a homozygous dominant allele in the population. 2PQ, we plug in our values we found earlier, 2 times P, which is 0.613, times Q, which is 0.387, multiply all those together, and we get 474, which is the frequency of having a heterozygous allele within the population. Q squared, which was already given to us, which is nice, is 0.15, 15% frequency of having the homozygous recessive allele. Our last question, kind of tying it all in together, assuming there is Hardy-Weinberg equilibrium, how many individuals out of 3,500 would be heterozygous? So this could tell us many things about a population, predict heterozygous traits within a population. So we just multiply 3,500 times 2PQ, which is the frequency of a heterozygous allele within a population, which we found to be 0.474, which equals 1659. So in a population of 3,500 people, we would predict that 1,659 of them to have the heterozygous allele. This is how you do a Hardy-Weinberg equation, and it is a lot simpler than most people think. So I hope you learned, and goodbye.